Welcome to July 29th LeetCode Challenge 01 Matrix. Given an m by n binary matrix, Matt return the distance of the nearest zero for each cell. The distance between two adjacent cells is 1. So you're given this matrix here, Matt, and you have one in the middle and surrounded by all zeros. So let's kind of put that to a form that we can see over here. And then we have the output right here. So what you want to do is, I'll just copy that and put it right there. Alright, so we have a 1. So let's start off with this matrix here. We have a 0. 0, the closest 0 to 0 is 0. So therefore we return 0. Alright, it doesn't specifically say it somewhere. But there is a 0 there. So if it's 0, then the closest 0 to 0 is 0. So therefore it's 0. It's a weird way of saying it, but for instance, and then we move on to this. See this number, the cell right here, has a 1. So the nearest cell that has a 0 will be either to the left, up, right, or down, and therefore it takes 1 step to get there because the nearest adjacent cell is worth 1 step. So therefore it's 1. And that's pretty much it. Let's copy this example here and see how it goes. So we start off with a matrix here. Actually, I'm just going to change this all to 1. They're much easier. And then the output is basically the same. I'll explain it. So, likewise as before, 0, the nearest 0 to 0 is a 0, so therefore the output for that cell is 0. And we have the cell here 1, the nearest 0 to this 1 would be we take the adjacent step to the left, up, or right, and that'll be 1. Likewise with this corner piece right here, the nearest 0 to the shortest path to 0 would be a step of 1, which would be upwards, and this 0 is 1 right here. Take 1 step up, then it'll be a 0 as well. And then therefore the 1 step is what this output would be. However, this cell right here, the one that's surrounded by a 0 to the left, up, and right, and there's nothing at the bottom, it actually takes 2 steps to reach a 0, the shortest, the closest path to a 0. How is that possible? You can take the left here to this 1 and take a step up 1. So therefore it's 2 steps. You can take it up, left, up, right, right, up to reach a 0, and those are all the equivalent to 2 steps. And therefore the cell here returns a 2. So that's the overall gist of the idea. And so we know how each time we take a step, it's basically we're doing like a kind of a branching of some sort. So we actually treat each cell as a node. We're gonna kind of look at this as a breadth first search algorithm, and we store all of our cells into a queue, and then every time we visit a cell before, we just store that into a set. And then we're just going to update our queue and update our set, and then do a breadth first search algorithm, and then check and see if it's 0. If not, add increment the count, and then continue our loop. So that's kind of our approach and our intuition behind it. So in order to make that work, we're going to initialize some stuff. The first thing I'm going to initialize is the row. So length is going to be the length of the matrix. I'm going to initialize the column, which is going to be the length of the matrix at index 0. Next thing I want to do after that is develop a queue. So I'm going to use a double-ended queue here. And then after that, we want to iterate through our rows, and nested row and columns, and then we're going to find each matrix index ij location is equal to 0. Then we're going to store that into a queue. Let's do that. For I in range of row, for j in range of column, we're going to loop through the matrix in the ij direction to find if the matrix at index I, j is equal to 0, right? If it is equal to 0, great. Q dot append our tuple of I and j. You're going to append our coordinates. So double quotes, double braces here. Alright, we have that going. We have a queue developed. Next thing we want to do is define a visited set. So we call it visited, and it's going to be a set, and we're going to update our set actually with visited.update and we're going to update it with our queue. Right, we're going to put all the information we have in our queue and all the zeros at each index location, each cell location into our visit set, because we don't want to visit that if it's already a 0. And then we're going to have something called a step counter. Our counter, we call it count. It's going to be 0. So this count is actually going to keep track of each time we take a step. We move from one cell to another. That's so that we can keep track of our distance, right? And we call it distance too. We call it distance count. We call it step. We call it whatever, right? It's a distance counter. So this is actually our meat of. So we have everything kind of initialized, defined, and queue developed and visit set developed. Next, we're going to do is to actually write our breadth first search algorithm. So here's how it's going to be done. So while queue exists, what we're going to do is for each cell called blank in range of length of the queue, we are going to find our x and y coordinates by popping the last item on our queue. So queue.leftPop. Pop left, I mean, what am I doing? Left, pop left. Alright, so we have our ij coordinates from our queue, that last one, and then for each direction that we want to step in, we want to take in now we need to find our direction that we're going to take a step in. So let's call it delta y and delta x. So delta x actually and delta y. A little bit of calculus joke for you guys, and we're going to store that into our coordinates. So we're going to have take a step to the left. So that would be coordinates 1, 0. We're going to take a step to the right, -1, 0. We're going to take a step upwards, so it's going to be 0, 1. And take a step downwards as well, 0, -1. So these are all the potential steps we can take. I'll erase this right here. Right, for each step we could take in the x, y direction, up, down, left, right. And then for that, what we want to do for each of those, we want to find our new x, y direction. So our new x and y is going to be actually our x plus our change in x, so x plus dx. So I'm going to call it new x, new x, new y, and it's going to be, for new x, it's going to be x plus dx, and for new y, it's going to be y plus dy. Changes in y, I should say. Clever naming scheme. So if we want to look for a boundaries condition now, a boundary condition. So what does that mean? So if, for instance, if we are this location here, we can't take a left, we can't go down because it's outside the boundaries of our matrix. So we want to make sure we avoid that. So here's how we avoid it. So if new x is less than 0, or new x is equal to the row because it's reaching a boundary, or new y is less than 0, or new y is equal to our column, then these are the boundary cases, and we want to continue. We don't want those numbers. Continue. Likewise, if our new x and new y is in our visited set, then we're going to continue as well, because we don't want to visit, we don't want to look at x and y coordinates or that are already in our visited set, because they serve us no relevant information. Right, we don't want to look through them again. We're going to continue this as well. Alright, let's see what else. So after those, we're still within our for loop. We need to update our queue and update our visit list. So how are we going to do that? So we're going to do queue dot append, and we're going to append our new, because at this point we generated our new x and new y because we're taking a step in each direction, and we're going to put that into our queue and put that into our visit set as well. New y, because we don't want to look at them again afterwards. Oops, visited dot add, and we're going to add new x, new y. right? We don't want to look at things twice because we already looked at them. So we just exit this for loop. What are we going to do next? So there's two conditions we're looking for. So either it's a 0 or it's not. So if the matrix x comma xy is equal to 0, then what we're going to do is update the matrix at the x and y direction to be 0. Because remember what I said before, if a cell is 0, the nearest 0 to a 0 is 0, so therefore the output for that cell is 0. Right? Else, we want to update the matrix at xy location to be the matrix at xy, the number at xy, the value at xy I should say, at the cell, to be count plus count minus 1. And for here, we want to increment count, right? Because every time we take a step, we want to increment that, and then at the end of the day, we want to return our matrix. All right, let's run the code and see how it works. Okay, it looks the same. Submit. All right, accepted. Awesome. So basically, the first thing we did was define the rows and columns, and we made a queue. We iterated through each cell of the matrix to find the zeros, and we pinned that to a queue. We also developed a set, and this is where we're going to keep all our cells as a 0. And then we have a little count or step counter variable to measure the distance of how many times we take a step. And this while loop here actually enters our breadth first search algorithm, looping through each element in our queue. We're going to find an xy direction for it, and then we find whether the x is equal to 0 or not. If it's equal to 0, then return 0, right? Then we're going to update the matrix. It's going to be our output. If not, we're going to add the count right here. This minus 1 add 1 thing, I think it's a little bit of a memory thing where you have to minus a 1 because you haven't added the 1 yet, right? Because you're going to add the 1 down here, so it's a neutralizer. However, we also made a new xy location that we're going to search next. So each time we take a step, we actually make a new xy location, and then we put that into our queue, into our set, and then we just continue looping through it using a breadth first search algorithm. Alright, so that's pretty much it. Time complexity is big O of row times column, because we have to iterate through the rows and the column. So since new cells are added to the queue only if their current distance is greater than the calculated distance, the cells are not likely to add multiple times. So we have visited queue, so things are not added multiple times. Space complexity is also big O of row times column, because additional space complexity is required to maintain this queue right here. Alright, that's pretty much it. You need to know have a good background using a breadth first search algorithm, but otherwise it's a nice one. Alright, have a great day, guys.